everybody. We're going to go ahead and let folks start coming into the room. In the meantime, go ahead and let us know in that chat box at the bottom of your Zoom screen whether or not you've joined us for a webinar before. I'd love to see who's new, who's returning. We are so grateful for you taking your time out of the week to spend this afternoon with us. So thank you so much for being here.
Yeah, hi, everyone.
Hello.
Thanks for coming. Yay, Jennifer's been with us before. That's exciting.
Welcome back.
Anyone else done a webinar with Vernier before?
Nice.
Oh, some new folks. New folks. All right, cool.
Awesome. We are having some good weather here in Oregon for the first time in months, it seems like. So I hope everyone's having some nice springy weather, if that's what you're hoping for.
For sure. It's been a long winter here.
Yes, amen. All right, well, it looks like it's time to go ahead and get started. Before we dive into everything, I do have a little bit of housekeeping to knock out. I'll pass it off to Dr. Melissa Hill of Vernier Science Education and Dr. Tim Pashkowitz of Pine Research here in just a moment. But first and foremost, I wanted to let you know that the recording of this webinar will be available on our website. You will also get an email with the recording in it. As soon as that's on our website, it typically takes about a week or so to get that online. So keep an eye out in your emails for that. We will also be sending you a link to the resource folder with all of the information that we'll be discussing today, and I'll drop a link to that in the chat as soon as I'm done talking. So that's coming your way. I would love to answer your questions during today's session. Please drop your questions into the chat box. Both Tim and I will have an eye on that chat box and be answering your questions. But if there's something we don't get to, we will definitely follow up with you afterward. And last but not least, before we dive into the webinar, Melissa is really quickly going to chat about an upcoming chemistry and biology webinar we'll be doing in May. And with that, take it away, Melissa, and enjoy the webinar, everybody. Thank you so much.
Thanks, Dylan. Yeah, hi, everyone. Yes, I am Melissa Hill, and I'm one of the chemists here at Vernier. I've done a lot of these, and we are doing another one coming up here in a couple of weeks. I don't have the exact date in front of me, but it's in a couple of weeks, and it's about sensor storage for the summer. And I know this is a huge topic for chemists and biologists alike, so I'm doing it with one of my biologist coworkers. So sign up for that one, sensor storage, get your sensors prepped before you put them away for the summer session. All right, yeah, so like I said, I'm one of the chemists here at Vernier. I realize we might also have some Pine folks in the audience, so I'm gonna do my full introduction. I'm one of the chemistry staff scientists at Vernier. Vernier is a pretty small company. We're around 100 people. And that includes, you know, people putting stuff in boxes, people who write our software, people who write our curriculum. So there's actually only 3 chemists that work at the company. So if you call up, you're going to get me, Noose, or Elaine. So we do stuff like the technical support. We do a lot of the trainings like this. I like to focus a lot on product development. And I actually helped develop this product that we're going to talk about today, the GoDirect Cyclic Voltammetry System. And we started working on this product kind of wholeheartedly, probably around 5 years ago. And we worked with Pine Research. And in fact, I worked directly with Tim. So I'm super excited that Tim is here, and I'm going to let him introduce himself.
Thank you so much, Melissa. As Melissa said, we did enjoy some good times developing this and testing it and figuring out how it's going to be useful. So I'm Tim Pashkowitz, and I'm from Pine Research, and we're on the other coast. So we're in North Carolina, and the weather was pretty nice here, I think, although I was inside all day. But I've been at Pine Research for about 11 years now, and it's a very similar, I think, environment as Melissa described for Vernier, but I think we're a bit smaller. if you add in all the manufacturing, maybe it's about 100 people. But here in North Carolina, there's, less than 15 of us, and it's mostly a group of electrochemists, software engineers, and a couple of electrical engineers. So like Melissa, I enjoy product development, applications development, and at small companies, we tend to wear a lot of hats. So I am here to support the webinar, and I'm really excited and hope you enjoy learning about what the CVS system can do.
Yeah. Thanks, Tim. And Tim is the electrochemical expert here, so definitely put all your questions in chat. He will get to them. He'll interrupt me as we go, and we want to get all those questions answered because ultimately we're here for y'all. So today's agenda, we are going to be talking briefly about electrochemistry and cyclic voltammetry. But the majority of the webinar is going to be spent using the GoDirect cyclic voltammetry system. I'm going to be demoing a couple of experiments for you. We're going to show you these screen printed electrodes. I'm going to show you the free software instrumental analysis that you use with this system. And in the process of that, we're going to be demoing 2 experiments. The first one is determining acetaminophen concentration in children's Tylenol. And the second experiment I'm going to demo is kind of an inquiry style experiment that really goes over the basics of cyclic voltammetry and getting a good voltammogram. And that is going to be while looking at the reduction of ferrocyanide. And then we're going to go over some other applications that are appropriate for high school, for college, and answer, of course, all your questions. Everything I'm going to be going over, all those experiments, all those protocols are in this shared Google folder. There's sample data, there's lab instructions, and hopefully Dylan can put that link in the chat for you all so you can access it as soon as possible. This slide deck is in there as well. And then that's why there's so many live links in it. So you can go to the slide deck later and click on those. All right, starting off. So I've got to be totally honest. My PhD is in time-resolved laser spectroscopy. I am not an electrochemist. I know very little about electrochemistry, or I certainly did before I started working on this product. And when we started working on the cyclic voltammetry system about 5 years ago or so, I didn't really hear of a lot of certainly not high school, but even undergraduate level educators getting into cyclic voltammetry or even really heavy into electrochemistry. They were just doing electroplating or looking at half cells and stuff like that. But I got to tell you, the last couple of ACS meetings I went to, that is all anyone can talk to us about. Everyone is adding electrochemistry to their Gen Chem, to their AP Chem at the high school level, to even younger. And they want more robust, more hands-on experience with electrochem. And I'm citing this article that just came out in the Wall Street Journal, but basically with this focus on green technology and companies needing to hire electrochemists and chemists who are well-versed in electrochemistry, educators have got to incorporate this more and sooner. We got to follow with where our students are getting jobs. So I think that's why we're starting to hear a lot about it more, and hopefully this webinar will help you get some more robust resources into your classroom for your students. We are going to be doing cyclic voltammetry today. I'm not going to do background on what cyclic voltammetry is. I have some great resources here for you. The Pine Research website is amazing for all things cyclic voltammetry. So I recommend their resources on their website, and also this great JChemEd article here that gives you, a practical beginner's guide to cyclic voltammetry. I think I read this about 4 times when we started working on this product. It's a really, really good article. Okay, so we are going to jump in. I'm gonna change my screen up a little bit here. So this is live. This is me. So we're gonna talk about, give you a little tour first of the GoDirect cyclic voltammetry system. And you might hear us say every once in a while CVS. That's kind of short for cyclic voltammetry system. And it really is a whole system. It comes with more than just the box. So this is the box itself. This is the system, but it also comes with 25 of these screen printed electrodes. And we're going to get pretty in depth with what these guys are and how they work a little bit later. But it comes with 25 of them. They are disposable. And when you go to replace them, they're about $4 each. It comes with 4 of these scintillation vials. These are super standard size scintillation vials, so you can use whatever you have on hand or purchase extras from other companies, but it does come with 4. It comes with this stand, so you can hold everything together while you're taking data, which you'll see demonstrated soon. It comes with a micro USB cable for charging and data collection if you want to take data via USB. But all of that comes in one of these boxes. And then it comes with 5 free experiments. And of course, a very robust, nice user manual. And Vernier is trying to get away from wasting as much, wasting paper. So those experiments are not printed out. You do not get a book with purchase. They are electronic resources that are in your Vernier account that you log on to vernier.com and log into your account. And then you'll see those electronic resources in your account, and they're available in their Word format so that you can edit them, photocopy them, distribute them as much as you want. The previews for those experiments are on the website, available for free in their full form, but they're in their PDF version. And then of course, today you get access to that Google folder that Dylan put the link into chat, and those have the 2 experiments we're going to do today in their PDF forms. And I don't always recommend the user manual for our Vernier products. Sometimes it's really kind of short and sweet, but the cyclic voltammetry system has a really nice, robust user manual that really goes through every detail about what all the settings mean. So I highly recommend it as well. And then it comes with free software, Instrumental Analysis, and that runs on Windows, Mac, iOS, Android, and Chrome. It's also compatible with LabQuest 2 and LabQuest 3 if you're a LabQuest user, but make sure your software is up to date. So like I said, it really is a full system that you get. Here at Vernier, we really like to make sure you have everything you need right out of the box. So let's get started. So this is Instrumental Analysis. Again, this is a free piece of software you download from our website. It takes data from the Vernier Mini GC, any version, takes data from the GoDirect polarimeter, and it takes data from the GoDirect cyclic voltammetry system. So first thing first, I need to connect my system to the software. Like I said, if I want, I can connect via USB. So I can plug the micro USB side of the cable into the system, and then the standard side would go into my computer or my Chromebook. But I can also take data via Bluetooth, and that's what I'm going to be demonstrating today. So in order to connect via Bluetooth, I press the power button here. And now my Bluetooth light is going to start blinking. So it's broadcasting, it's ready to connect. I don't want to connect anywhere except in the instrumental analysis software. I don't need to go to my device settings. I don't need to do any of that stuff. In instrumental analysis, I click this button here, connect an instrument. And now it's searching, and you can see discovered wireless instruments, the GDX CVS, and that serial number is the serial number right here on this label. So if you have multiples of them on at one time, you can find which one you want to connect to. Press connect. And now it's up here in my connected instruments. And I say done. I'm going to take voltammetry data. So I click on voltammetry. And you'll see right away I'm plopped into this great little setup where I can set up my whole experiment. The cyclic voltammetry system can do 3 types of voltammetry experiments. So it can do cyclic voltammetry, which is what I'm going to demo today, but it can also do open circuit potentiometry, and it can do bulk electrolysis. So one of those free experiments that does use the bulk electrolysis mode, and it actually plates these screen printed electrodes with metal, so you can measure them before and after and do your Avogadro's number calculations and all that cool stuff. So that's a really good experiment in our 5 free experiments. But we're going to do cyclic voltammetry. So this is my cyclic voltammetry profile. The default profile here is actually designed for the first experiment in the book, which is the determination of acetaminophen concentration in children's Tylenol. So we're going to figure out how much acetaminophen is in one of these bottles of liquid children's Tylenol that you get from the supermarket. And to do that, we're going to run a series of known standards of known acetaminophen concentration, make a calibration curve, measure our unknown, figure out the concentration from there. So this first experiment is really using the system as a tool to learn something about chemicals. So I'm going to use my default settings. I do know I need to change my current range to medium, just to accommodate my concentrations that I've made. That is a step in the procedure, and it's all good to go.
And quick before you hop into the experiment, we do have a question really quickly. Can the CV device be accessed via the Python API?
That's an excellent question. As you can tell by my pause, I'm not 100% sure. I'm 90% sure you can't right now. But I will double check on that. And if you send that, either ask that email or send an email to chemistry@vernier.com with that question, or if Dylan gets your contact info, I can follow up with that. But I'm not 100% sure, so I don't want to say, but I'm pretty sure it's not right now. Okay, so now we got to get the system set up. So first, I take the screen printed electrode here, and this I'm going to use a new screen printed electrode and plug it into the port. That's it. That's all there is to it. And then I'm going to take my 1 millimolar acetaminophen solution in my scintillation vial, put it in my clips, and pass the SPE into the solution and kind of snap the system into the stand. So it all snaps in. And then I'm going to go ahead and press collect. And now data is coming in and it's collecting, and I can tell it's still collecting because it says stop. And when it goes from stop to collect, then it'll be done. So the screen printed electrode here, as I said, they are disposable. But you can use them multiple times. You don't have to do just one run and throw it away. That would be very wasteful, and we're not about that. In general, we say use one screen printed electrode for like the whole experiment. So all of our acetaminophen solutions and my unknown, I'll use all of those with the same screen printed electrode. So typically the whole class period can use one. And so especially acetaminophen is one of the stickier substances, so it does really depend on what you're using. The acetaminophen is pretty sticky, so one class period is all you're going to get out of it. Something like ferrocyanide, you could probably get away with maybe using it a couple of class periods or all day, depending on how many trials are run. But you can get a lot of use out of these screen printed electrodes. All right, so my CV is done here for my 1 millimolar acetaminophen. So I'm gonna, you can tell that's kind of tiny, right? Can't really see it. I want to zoom in, so I'm going to double click on my graph. And now I can see my very pretty duck, right? It's a pretty good duck for acetaminophen. Okay, so I have current versus voltage. I'm going to run a series of these. So I want to change the name of this run and make sure I'm noting that it is 1 millimolar acetaminophen. In order to do that, I click on my current axis label here, and that is data set 1. The little ... right here is going to let me rename my data set. And in here, I'm going to say 1.0 millimolar acetaminophen and rename. And so now I have named that run. So I'm going to repeat this process for my 0.8 millimolar acetaminophen solution. And I am going to dab my screen printed electrode with a chem wipe to just get the big drops off of it. And again, I'm using that same screen printed electrode, snapping it in and press collect. So you can see in the software that the previous trial, it didn't get deleted. It is just hidden in the background. I can go and click on my Axis label and see that that data set is still there, my 1 millimolar, it's just not enabled. And while my 0.8 millimolar is coming in, I can rename, just kind of a nice thing. And there's my 0.8. Finish that, double click. And now if I want to compare my 1 millimolar and my 0.8 millimolar, make sure that they're coming in the way they need to be. Turn on a graph legend, I can see, oh, this might be a little bit tiny on y'all's screen. So I can go up here and click into this little dot up here and say presentation, and I can click to 1.25. So if you're demoing this in front of a class or what have you, you can always edit that presentation mode. So hopefully you can see that a little bit bigger now, my graph legend, my Axis labels. And I'm going to go ahead and do, I'm not going to do all 6 of the runs that the lab calls for. I am going to do one more. I'm going to do 0.4 millimolar. While I set that up, Tim, are there any questions or any interesting comments that have come in?
We've had a question that you did address it, and just to follow up while you're working on that, it's a great question that comes up a lot with screen printed electrodes, and they have a lot of strength in that they're easy to use and low cost as compared to traditional electrodes, but they do have a lifetime. And I think you addressed in the same way that I answered it, as if we rehearsed this or something. But I do think it's important to note that the nature of the chemistry is really what's going to dictate how long they can be used. Like Melissa's doing here with the acetaminophen, after several hours of doing this, that acetaminophen's got these nice conjugated bonds and it loves to lay down on carbon. And so over time, the electrode becomes poorly responsive to anything, and that'll dictate its use time.
Yeah, great question. We get that one a lot. So, okay, well then let's keep going. So I did three runs. Again, the lab calls for doing several more so you can get a nice robust calibration curve. But I'm going to stop there. You guys get the point. Do this with more concentrations. The value that we care about for our calibration curve is, of course, the concentration, which we know because we made these standards. But the second value we care about is the peak current. So in order to obtain that from the graph, we want to click on this graph tools in the lower corner and click on view statistics. So you can see this is where I also came in and turned on a graph legend. I can edit the graph and put a title in there. I can do several other things in here, but statistics is typically what we want with CV. And you can see when you turn on the statistics, you get information for the whole entire data set. I get the number of samples that the data set contains. I get the average. I get the minimum current and what voltage that occurred at. So that's this peak down here. And then I also get the maximum current and what voltage that occurred at. So that's this maximum peak up here. So again, we want the maximum current. So for my yellow trace, which is the 0.4 millimolar acetaminophen, my max occurred at 26 microamps. So I'm going to write this down and I'm going to make a table And actually, I've done something pretty nice for you in that Google folder. Not only do I have sample data in there, but I also have this Google sheet that has all the calculations for doing your sample prep, because I know we all love making cereal dilutions. So all those calculations are in there. You can adjust the volumes, et cetera, et cetera. And then that's to make your series solutions. But then I also have all of the calculations for doing the analysis. Now, this is not something I would give my students, right? Because it kind of gives away the answer. But I think it's nice as educators to kind of, when you're quick making solutions and you want to double check that everything's coming out the way it's supposed to just be able to put those values in the table, check the slope and intercept, and make sure you're getting a decent calibration curve. So again, I would put this max current 26, and for 0.4, that's exactly what I got yesterday, so I'm not even going to mess with it. And you put all these in, you graph them, you get your line, and then you measure your unknown, right? Your children's Tylenol. And there is some tricks to making the dilution for this as well, so make sure you read the instructor notes. You just have to dilute it. It's too concentrated as it is in the children's Tylenol. So when you take all those factors into account, you determine how much acetaminophen is in there, and then you can determine your percent errors and all that good stuff. So that is that first experiment with acetaminophen in children's Tylenol. So like I said earlier, that is a really good experiment for just demonstrating CV as a tool. Cyclic voltammetry is a tool, just like you would a spectrometer and doing Beer's law to determine the concentration of copper sulfate, in an unknown solution. You can use CV to determine, the concentration of acetaminophen in children's Tylenol. So it's very much using it as a tool. So teaching your chemistry students that they have multiple tools at their disposal, because these are clear solutions, is a great way to do that, is a great use of this product. But the next experiment is actually going more into teaching what CV is and how to get a good voltammogram. So I'm going to set up for that with ferricyanide, which is a tried and true chemical that electrochemists use. Again, I'm just blotting in between runs. I'm using the same screen printed electrode. I'm not even going to switch it right now between acetaminophen and ferrocyanide. And I'm going to set all that up. And then I'm going to show you real quick in the slide deck kind of the goal of this experiment. Like I said, it's inquiry style. So you have the students go into those CV profile parameters and change them one step at a time, very systematically, so that students understand that they don't get a pretty duck just with default parameters every time. They get a very, I don't even think you could call this a duck, but you get, and then you change one parameter at a time to get nicer and nicer data. So because I've done this once or twice before, I happen to know the profile that will give me the best data. And that is a 2-segment CV that goes from 600 to -600. And I'm going to do it at a 25 sweep rate, so it'll be nice and pretty, but also so that you can just see how the graph comes out when I change all these parameters. And I'm going to put the current range to high. So I've changed every single parameter I could from the acetaminophen, and I'm going to press collect. All right, so this is going to take a while to come in. Did we have any have any questions, comments, Tim?
Yeah, I was just following up with Joe had a question, just trying to get more of a figure of merit, I think, on how long, what is her specific question is, what is the degradation of data we would expect to see from a screen printed electrode? And again, it's very intimately tied to the chemistry, but she specifically asked about this experiment. And my anecdotal response was, when we demonstrate this at a conference,
Yeah.
for 6+ hours, that single electrode is useful in that range.
Yeah.
I think a lot of it will get back to how analytical and quantitative the goal is for the course. If
Right.
this is exploration, then one electrode could be used a very long time, understanding that the response is going to shift quite a bit over time.
Yeah.
So just to sort of, I'm not answering directly because it's kind of unknown. There's a lot of variables, but again, I think that gives an idea of how useful these are.
Yeah. And I will say, because I don't change them very often at all. But if you are trying to determine, just like Tim said, the nature of the experiment, if you just want students to play with acetaminophen or play with ferrocyanide and explore the parameters and all the data you're going to get, then you could use the same electrode for a long time. But if you really want to determine the amount of acetaminophen in children's Tylenol, if you keep that same screen printed electrode for 3 class periods, you're going to get a lot higher % error in that 3rd class period than you are in that 1st class period. They're still going to get a duck. They're still going to get a shape. They're still going to get something that they can determine a peak current from, but the error is going to be higher. So hopefully that helps with some of that.
Yeah, and real quick before you start, PJ asked a question, and I'm not sure what level of control is within instrumental analysis, but it's how many samples per second. Is that a parameter in the settings, or is that set by your software?
Right, it is not. So for CV, it is not. Obviously, the other settings are just looking at voltage or just looking at current. And so you do set those in the software. But for CV, the rate is determined by your sweep rate here. So millivolts per second is what is setting the rate of data collection. Yeah.
And to answer, he had one follow-up question for everyone. He asked, is this a step pause voltage sweep or a continuous sweep? The answer is yes and no. CV is continuously changing the potential over time, but this is a digital instrument. So we've quantized these steps. So it's not a true linear sweep. There's small little series of steps across a sweeping boundary. For all intents and purposes, we would call this a continuous sweep. But truthfully, there are little micro stair steps that are creating the sweep.
Awesome. Great questions. I'm so glad you're here, Tim. All right. And here's our beautiful ferrocyanide duck that we got from doing lots of changes of our CV profile to determine how to get a very pretty CV duck for ferrocyanide. Okay, and then the experiment goes on to have you do it at different sweep rates. So you can come in a lot faster. So I can come in and do this at 500 millivolts per second. And it's going to come in real fast. And how that changes your CV. And you can compare it to your 25 sweep rate. And all that good stuff. So you can do those types of experiments as well with the GoDirect cyclic voltammetry system. So I think so that's all I'm going to demonstrate. Is there any other questions about the demonstrations or the experiments I went over before we get into kind of frequently asked questions? So what is the voltage and current resolution from PJ in there?
Yep, I was actually just doing some calculations. So PJ, these are 16-bit digital to analog and analog to digital converters that are used in the system. So I was just about to do the math for you to tell you the theoretical values, and I'll put them in chat.
Yeah, great. Yeah, I was wondering if that was something. It doesn't look like that's on. I thought that would have been on the website. All right. So frequently asked questions. We've already talked a lot about these screen printed electrodes. But again, we'll just mention they are carbon. And they are carbon based, and they have a silver chloride reference electrode system on there. And for those of you who are familiar with Pine Research, you may be looking at these and say, hey, I recognize those. Pine does make these for us. They are the same ones that Pine sells. So if you already have a bunch of Pine carbon electrodes, you can use those with the cyclic voltammetry system. And then you say, well, I have some systems I want to investigate that have, are non-aqueous or different things that you need, maybe Pine's ceramic electrode for, or something like that. The cyclic voltammetry system is compatible with Pine's other screen printed electrodes. And we do have in this link, we have the ones that they are compatible with and how you can purchase those through Pine. So if that's something that interests you, check out that page on our website. But be aware of the limitations of the cyclic voltammetry system. Not everything that you would do with a ceramic screen printed electrode, for example, is something that can be done with the cyclic voltammetry system. So make sure you're aware of the limitations of the system. You may not be able to use our system for that chemical reaction, for example. All right, so into other common applications. So high school really is kind of doing that Tylenol, acetaminophen experiment and doing the electroplating experiments. There's also an Ohm's law experiment in the 5 free experiments that are all very appropriate for high school. And most of the people who are using this in high school, that's what I see them doing, kind of using it as a tool to just show their chemistry students the breadth of tools out there that chemists have at their disposal to learn about chemical systems. In college, of course, Gen Chem, same idea. But as you get kind of into upper division courses, you're getting into that second experiment where you're really talking about cyclic voltammetry systems. Maybe you're talking more about the redox reaction, the chemical properties going on, the anode versus cathode side of the reaction, and what, looking at the Tylenol CV versus the ferricyanide CV are very different ducts. Why is that happening? So you can do all that in like your physical chemistry, your analytical chemistry, your instrumental analysis courses. Your inorganic chemistry is really where I see this system being used a lot in undergraduate school. Lead in water is another one that we get requests about a lot. You can do it with this system. We do have a protocol written for it, but it uses mercury. So be aware of that. That's why it's not one of the 5 free experiments, because a lot of schools can't do that. But you can do it with this system. And if you're not quite ready yet for the cyclic voltammetry system, you're like, really, we're just, we want to do some titrations with orange juice or look at Avogadro's number. Vernier has options for that. In fact, back in February, we just did an electrochemistry webinar on half cells and all that kind of stuff with the Go Direct voltage probe. We also have a constant current system, which is great for electroplating, Avogadro's number. We also have an oxidation reduction potential sensor, which is good for that ascorbic acid and orange juice titration that a lot of people want to do with electrochem. and then the CVS. But if this is too limited for you, Pine has a true potentiostat that is also appropriate for the undergraduate level. And I'm going to let Tim talk about this.
Well, I think it's funny that you call it a true potentiostat. That's not to say that the GoDirect CVS system is not. It's just to make it affordable and available to different areas of education. We had to take out some of the heavy hitters. So it has a lower current and voltage range on purpose, but we wanted to make sure it could cover the essentials. So to Melissa's point, very often there could be interest by students, or there could be faculty who want to do some independent research projects or take some of these fundamentals that they've learned with cyclic voltammetry and start progressing. They may require higher current, higher voltage, their own electrodes. And when you get to that stage, you've sort of outgrown the CVS at that point. And so we have a product here called eChem in a Box. As Melissa said, you'll notice the same screen printed electrodes because that's very popular even with this system. And this costs quite a bit more than the CVS. So there is a bit of a gap between what Vernier offers and then what we have here with eChem in a Box. But I just wanted to let you know that if you were progressing up or wanted to make it more a major part of an analytical course, let's say with a lot of quantitative work, then you may want to progress to something like this.
Yeah, absolutely. And then I also had the opposite with some discussions at recent ACS. A lot of people maybe already have this system and it's a little bit of overkill for some of their courses. So if you're already familiar with the Pine system and you know you only use it for one experiment, save the eChem in a Box, the Wave Now, for your upper division students, and then you can incorporate the cyclic voltammetry system with your younger students. Okay, yeah, the eChem in a Box. So Tim, there's around 5,000, and the cyclic voltammetry system is 1,000. So those are the costs we're talking about. All right, I think we got through everything. So I'm gonna let Tim answer that one there. Python API.
Yeah, at this time, we actually don't offer any APIs for any of our products. It is becoming more and more requested. And I can't speak to Vernier's perspective, but from ours, we you know, and software engineers know exactly all of the system and how to communicate with the hardware. And so it's if they write software, then they can ensure that your experience with it does exactly what you want, unless it's not what you want, and then you need an API. So we do encounter this quite a bit, and we don't offer any APIs at this time, but it is a highly requested feature.
Yeah, and like I said earlier, Vernier, we do offer Python APIs, but typically our more advanced instrumentation, we don't, just for the very fact that Tim said we want the user to have a good experience. But I will follow up to see if it does work. But I'm pretty sure the answer is no. Yeah, any other questions? Throw them in chat. We have a couple more minutes left. I will, if you process, this was a lot of information. We went over a lot of stuff. So if you process it, you have questions later, definitely email chemistry@vernier.com. Pine and Vernier have a great working relationship. So feel free to shoot all your questions at me at chemistry@vernier.com. I reach out to Tim when it's beyond my level of expertise. Again, I already told you I'm not an electrochemist. That's what I have Tim for. And we get all your questions answered. Just shoot them to us first and we'll get your questions answered. If you have an application that you want to know if it will work, you can email that to chemistry@vernier.com and we'll work through it. But another great option is Vernier offers free 30-day previews on all of our products, and that includes the Cyclic Voltammetry system. So if you'd like to do a 30-day free trial of the Cyclic Voltammetry system in your own classroom, in your own laboratory, with your own chemicals, just shoot me an email, chemistry@vernier.com, and I can set that up for you. You can also give us a call. You can also reach out to us via chat. The Google folder, yep, Dylan just put it back in there, or no, sorry, that's her feedback. But the Google folder has this slide deck, which has a lot of live links. There was a lot of questions about getting the resources here and there. A lot of the live links in the slide deck will get you to those resources or those web pages that I referenced on our website. So definitely check that out. Thank you again, Dylan. And yeah, if there's no other questions, Dylan, do you have some parting words? You want people to fill out a form?
Yeah, I went ahead and dropped a link to a quick survey that you can take there in the chat. I would love to hear what you all thought about today's webinar. So please head to the chat, click that link to the survey, and give us your feedback. But with that, I think we are wrapping up. Thank you all so much, and we hope we'll see you again soon, preferably next month for our upcoming webinars. So, all right, bye everyone. Thank you.
Bye. Thanks, everyone.
Thank you.